Welcome to The Explainer. Today we're taking complex inorganic chemistry and breaking it down into the intuitive, dynamic rulebook that literally governs our entire physical world. Have you ever wondered why a chunk of sodium explodes the second it touches water, while the gold in a wedding ring can just sit there, perfectly untouched, for centuries? Well, it's not magic. It's actually just the rules of the game. And today we're going to unpack exactly what those rules are. Okay, so here's our roadmap for The Explainer. We're breaking these atomic battles down into 5 steps. First, the periodic code. Second, metals versus nonmetals. Third, the reactivity hierarchy. Fourth, compounds and electron exchanges. And finally, exceptions and everyday impact. Let's dive right in.
Section 1. The periodic code. The hidden mechanics of the elements.
Everything you touch, breathe, and interact with is governed by a hidden code. And it all starts with the fundamental currency of the universe, electrons. Now, the key concept here is electronegativity. Electronegativity is simply the ability of an atom to attract those electrons to itself. Think of it like an element's intense, deep-seated electron hunger. This hunger fundamentally drives how reactive a given element is going to be. Some atoms are absolutely starving for electrons, while others, well, they're practically giving them away.
And you can actually see this hunger mapped out beautifully as opposing directions on the periodic table. Notice what happens as we move down a group. The atoms get, well, kind of bulky. The atomic size increases, and because the atom gets so physically large, it just can't hold on to its outer electrons very tightly. So its electronegativity and the energy required to rip an electron away, known as ionization energy, both plummet. But if you look at moving across a period, the atom shrinks. It holds on to its electrons super tightly, meaning its electronegativity and ionization energy shoot right up.
Moving on to Section 2. Metals versus nonmetals, the electron givers and takers.
This is where the whole thing becomes a showdown. We've got the generous, electron-donating metals pitted directly against the aggressive, electron-stealing nonmetals. Metals inherently want to lose their electrons to form positive ions, which we call cations. Nonmetals, they want to gain them to form anions. Because metals have such low ionization energy, it's super easy to just take their electrons. Conversely, nonmetals are driven by their super high electronegativity. This basic fundamental divide literally dictates everything, from the types of bonds they make to whether their oxides end up being basic or acidic.
But hey, nature rarely deals entirely in absolutes, right? Caught directly in the middle of these two warring factions are the metalloids. These guys cleverly exhibit intermediate behaviors depending entirely on who they happen to interact with. Elements like silicon, germanium, and arsenic can form both ionic and covalent compounds. They are so adaptable, in fact, that their oxides can sometimes be amphoteric, which is just a fancy way of saying they can play both sides of the fence, reacting happily with both acids and bases.
Now, to see the absolute extremes of these factions, we just need to look at specific columns known as groups. Look at Group 1 metals, like lithium, sodium, and potassium. They are incredibly reactive and form really strong bases. But compare that to Group 17, the halogens, like chlorine and iodine. These are highly reactive nonmetals and just ferocious oxidizing agents, meaning they are absolutely desperate to tear electrons away from anyone else.
Which brings us to Section 3, the reactivity hierarchy, the battle for chemical dominance.
So, what actually happens when these powerful elements directly compete with each other? Well, we get a descending ladder of power, a hierarchy where top-tier metals absolutely dominate and displace the weaker ones below them. Potassium and sodium are sitting at the absolute top of the food chain, reacting violently with water and acids. Step down a bit to aluminum, zinc, and iron, and the reactivity cools off to a medium level. Finally, way down at the bottom, you've got copper, silver, and gold. Metals so unbothered and frankly snobby, they often refuse to even react with common acids.
And here is exactly how that hierarchy plays out in real time. Let's look at iron and copper. Because iron sits higher on our hierarchy than copper does, it aggressively swoops in and kicks copper out of the solution to claim the sulfate for itself. It's wild. Iron starts out completely alone, but ends up happily bonded to the sulfates, while the weaker copper is kicked to the curb and left isolated. We call this a displacement reaction.
This very same hierarchy is exactly why dropping a chunk of sodium into water literally triggers an explosive release of hydrogen gas. Because sodium is an alkali metal sitting at the top of the series, its reaction with water is shockingly vigorous. Similarly, any metal that sits above hydrogen in the reactivity series, like zinc, for example, will react with acids like hydrochloric acid to form a salt and, once again, release a whole bunch of bubbling hydrogen gas. All right, Section 4. Compounds and electron exchanges. Let's see what happens when these factions actually mix.
Let's zoom in closely on the actual mechanics of these battles, the direct exchange of electrons. It's a beautiful push and pull relationship called a redox reaction, where one element's loss of an electron is perfectly balanced by another element's gain. Okay, so oxidation is the loss of electrons. When zinc loses an electron, it becomes oxidized. And because it gave that electron away, it acted as a reducing agent. On the flip side, reduction is the gain of electrons. When copper gains that electron, it becomes reduced. You literally cannot have one without the other.
So, what happens when these elements bond with oxygen? Well, their inherent properties dictate whether the resulting compound will behave as a base, an acid, or an adaptable amphoteric oxide. Depending on who they are, metals naturally form basic oxides like sodium oxide. Nonmetals, true to their opposing nature, form acidic oxides, like the carbon dioxide we exhale every few seconds. And then, of course, we have the versatile amphoteric oxides, like aluminum oxide, which can confidently react with both strong acids like HCl and strong bases like NaOH.
It's a very similar story when elements react with hydrogen to form hydrides. Their core identity shines right through. The generous metals donate their electrons to hydrogen, creating ionic hydrides like sodium hydride. Meanwhile, the electron-hungry nonmetals are forced to compromise and share electrons, forming covalent hydrides like methane or ammonia. And fascinatingly, some metals form metallic hydrides simply by physically absorbing the hydrogen right into their structure, almost like a sponge.
Finally, Section 5. Exceptions and everyday impact. The rebels and the real world.
You know, what's really fascinating is that nature always has a few rebels that absolutely refuse to follow the standard rulebook. Group 18 noble gases are mostly chemically inert because their valence shells are already perfectly full, they don't need to gain or lose anything. But wait, even they have a rebel? Xenon breaks the rules and can actually be bullied into reacting by the most aggressive nonmetals, forming compounds like xenon bifluoride. We also have hydrogen, the ultimate shapeshifter, uniquely behaving as both a metal and a nonmetal. And remember copper and silver? They sit so low on the reactivity series they just completely ignore common acids?
So why does any of this matter? Because these microscopic rules directly provide us with the skyscrapers we live in, the food we eat, and the neon lights that illuminate our cities. We use iron and aluminum in construction specifically because their metallic properties resist certain types of decay while providing immense strength. We completely rely on nonmetals like nitrogen and phosphorus to formulate the fertilizers that literally grow our global food supply. And those chemically inert noble gases, we run electricity through neon and argon to create those vibrant glowing signs you see downtown. I want to leave you with a thought. Since these exact same rules of atomic hunger and electron exchange apply to absolutely everything in the universe, what incredible redox reactions do you think are keeping your own cells alive right now? I'll let you ponder that biological mystery. Because once you understand this chemical rulebook, how elements pull, push, displace, and bond based on their size and electron hunger, you realize you aren't just observing chemistry. Every time you take a breath, every time your cells generate energy, you are literally walking chemistry yourself. Thanks for joining me on this explainer, and keep exploring the elements around you.